Okay, let's start today's lecture. Um, in the last lecture, I have given you few examples to solve. So in these examples, you have to find the power factor and the parent power. So we already learned how to calculate the parent power and the power factor of the load. I also explained the concept of apparent power, that seems the network is uh, in a capacity to have that much power, but that part is contributing to the reactance of the network as well. And we have the resistive part, which is consuming the real part of the apparent power. And this parent power has the real power P and the reactive power Q in the network. So in this example, we solve the power factor and apparent power of the given load in the case when the applied voltage is in time representation form. So first we convert the load in the polar form. So, and we know that the difference between the voltage and current phase is the same as in the load impedance. So that angle is taken from the load as well. Because the value of current is not given, so we cannot calculate the difference between the voltage phase and current phase. So that angle is 33.7 degree. So we take the power factor of the load, which is cos 33.7 degree, and that is 0.832. Because the sign of this angle is positive, so it is a lagging power factor, and the load is inductive in nature. So from this impedance, we find the current drawn by this impedance if the applied voltage is given. So the applied voltage is 150 at the angle of 10 degree. So we put the value of voltage 150 at the angle of 10 degree, and we substitute the value of load 72.11 at the angle of 33.7 degree. So from this, we can find the value of the current drawn by the load. Now we take the two RMS value. One is the RMS value of the voltage, and the other is the RMS value of the current. Or we can take the peak value of these two to find the value of the current. So, so we can find the value of the power drawn by the load by multiplying these two values and dividing it by 2, because the answer is the same as we take the RMS value, because in RMS value how can we take the RMS value? Because we divide this by 150 by under root 2 and 2.08 by under root 2, and that will become 1 by 2. So that is 156 volt ampere. That is the parent power of the load. So that example is very simple, and I hope you are clear about it. If you have any questions, so you can ask here. If you don't have any question, then we will proceed further. So next, we have to calculate the power factor of the entire circuit seen by the source. Here we have the voltage given in RMS form. So it's not required to change it in the RMS form. Second, we have to calculate the power factor of the entire circuit. So it means that, for example, if we withdraw the load, or we consider the, if we consider the voltage source is supplying current to the network, and the network considered as a load. So how much will be the power factor of the load or the network? And we have to calculate the average power supplied to the network. So we have to solve the network impedance, which is the load impedance. So you can see that this J4 impedance is parallel to this 8 and minus J6 ohm impedance. So we have this J4 parallel 8 minus J6 impedance, and we sum up the series resistance of the network, which is 10. So we have 10 plus the parallel resistance of the network, and the overall result of this impedance is 12.69 at the angle of 20.62 degree. So as in the previous case, we consider the load angle as the angle between the voltage and current phases. So we calculate the power factor as a cosine of this angle. So this is the load power factor. So that value is 0.936, and that is lagging. And lagging means that the load is inductive in nature. Now we have given the RMS voltage, which is 40 at the angle of 0 degree. So we divide it by the impedance value. And when we divide it by the impedance value, so the RMS value is 3.152 at the angle of minus 20.62 degree. So the average power is very simple when we have the IRMS given. So we can take the IRMS square into the resistance of the network. So for the resistance of the network, How can we find the resistance of the network? So we have to split this impedance into the resistive and the reactive part. So this impedance is split. You just change the polar form to the rectangular form, and you will take the value of the resistance and the impedance of the network. So from this, you calculate the power, average power supplied to the load. So here there is a question that what's the difference between the average power of the network and the real power. So in fact, the average power and the real power is the same thing. So you can take this value as 118 watt, and also you can take this value, calculate this value from VRMS into IRMS, right? So from this way you can also calculate the value of VRMS, IRMS into power factor, and in this way you will calculate the average power absorbed by the network, which is 118 watt. So you can see that the average power we have calculated and the real power are the same thing. Is it correct? So we proceed to the next example. Next example is also very simple. So in this we have to calculate the power factor of the entire circuit. So, and we also calculate the average power delivered by the load. So this is the third example which I have given you as an assignment. So we repeat again the same process to calculate the total load impedance or the network impedance. So that impedance value is calculated as 7 at the angle of minus 13.24 degree. So that load is capacitive in nature because the sign is minus. So we can calculate the power factor of the load. So just take the cosine of this. That is 0.9734 leading power factor. And the same way we have given the RMS value. So RMS value is divided by the impedance, and we can find the value of the RMS current. Now we calculate the average power supplied by the source in two ways. Either calculate the real power supplied to the network by multiplying VRMS, IRMS with the power factor. So we multiply 30 with the IRMS and the power factor of the network, that is 125 watt. Or if we take I square of the RMS value and the resistive part of this load impedance, So that is also 125 watt. So I hope now you are clear that how to solve these examples. Now the topic left for discussion is complex power. So there is uh, the term we previously learned, which is in fact is the apparent power. So in apparent power, we have the two parts. Uh, we have the two parts. One is the real power, and the other is the reactive power. And I'll show you the concept ahead. That we have seen that this real power and the reactive power is in fact drawn from the resistive component and drawn from the reactive component. So that powers are correspondingly calculated from the square of the RMS current with the resistive component and the reactive component, and we got these two powers. And if we see this both power as a part which is named as apparent power. So uh, here we have the real of this S is I square RMS R and I square RMS X. So that complex power can be expressed in terms of the load as well. And in the form of the load, we have seen that that is equal to Vrms over Irms and theta V minus theta I. And S is equal to I square RMS Z or V square RMS Z conjugate, or it is in fact is Vrms into Irms conjugate. So now we have see this uh, concept that we have learned that the real power P and the average power are same and they are calculated in watts, and that much power is delivered to the load. So why we call it real power? Because that portion of the power is the useful part of the power, and that much power is actually dissipated across the load. However, the reactive part is in fact is not consumed. That part is only exchanged from the source to the network. You know that the reactive power is across the energy storage elements. So these energy storage elements store the energy, and there is no dissipation of power across them. So it means they are contributing to the energy exchange, and that is mentioned in the form of volt ampere reactive power. So we can call this as the sum of these two power as the complex power. So what about the reactive power? Reactive power in case of resistive load, you know, its value is 0, and we have the unity power factor across the load. And in case of reactive power less than 0, we have a capacitive load and leading power factor across the load. And for Q greater than 0, we have the inductive load and the lagging power factor across the load. So here we see that the difference between the complex power and the apparent power. So the complex power is in fact is the representation of the power in the complex form, right? Representation of the power in the complex form. However, we have the polar representation. We have the polar representation of this complex power, and the magnitude of this complex power is in fact is the apparent power, which is in fact is P square plus Q square under root. So if we are determining the capacity of our network, so in fact we are finding the apparent power consumed by the network, and that apparent power is found from the complex power formula, which is P plus JQ. So the power factor, we know that the real power divided by the apparent power, so that is the cosine of the angle between the voltage and current phase. So is everything clear here? So that is the power triangle. So we have the real power, the reactive power, and the apparent power, right? So that is the power triangle. And the angle between the real power and the apparent power is the theta. And cosine of theta is in fact is P over S. So this is in fact is the power factor of this power triangle. So actually, if the power factor increases, so it means that the reactive power contributing more, and hence there is an increase in the apparent power. So because this apparent power is in fact is the under root of P square plus Q square, right? Also, if we say that if we determine the load, so we have the resistive load which contributing to the real power, and we have the reactive load which contributing to the reactive power, and we have the overall impedance of the network which is in fact is the contributing to the apparent power. So the difference between the complex power is just the representation of this polar and reactive power. So if we represent the polar and reactive power in terms of P plus JQ, so it is the complex power, and if we are contributing it as a P and Q quantity, so that is the apparent power. So the only by adding the imaginary component here, if I add J here, if I write J here, so you can call this as the complex power. And by simply ignoring this and calling this as P plus Q square is the apparent power. So I hope you learn about this. Now there is the lagging and leading concept of power factor. For example, this is the phase of the current is 0 and the phase of the voltage is theta V. So theta V minus theta I is positive. Is the value of this angle is positive when the reactive power is also positive, and this positive sign means that the current is lagging the voltage, and that is the lagging power factor, and that means the inductive load. That means the inductive load. And in case if the difference between the current phase and the voltage phase is negative, so the reactive power is also negative and the power factor is leading, and we have a load which is capacitive in nature. So we will see a problem here, that the voltage across the load is given in time form, and the current through the element in the direction of the voltage drop is I of t 1.5 cos omega t plus 50 degree. So we have to calculate the complex and apparent powers, real and reactive powers, and power factor and the load impedance. So that's very simple. First, we have given the value of the value. That value is the voltage. That value is Vm, right? And that value is Im. So we divide this Vm by under root 2 to find the value of Vrms and Irms. Now, for complex power, we have Vrms, Irms conjugate, right? So we take this Irms conjugate minus 50 degree, and that is 45 at the angle of minus 60 degree, right? And how to calculate the apparent power? Apparent power is in fact is the magnitude of this complex power, and that is 45 volt ampere, right? So next we have to calculate the complex power in rectangular form. So we calculate the complex power in rectangular form, and then we calculate the real power and the reactive power. The reactive power is measured in volt ampere reactive. So that is VAR units, which is volt ampere reactive. So that is in fact is the reactive power. Next, we have to calculate the power factor, and we calculate the power factor with cos of -60°, and that is in fact is the voltage and phase angle. That is the angle of this complex power, right? So that is 0.5 leading, and we have the impedance value, voltage divided by current. So we have the value of the impedance, which is 40 at the angle of -60°. So that impedance is capacitive because the angle is negative. I hope you are clear about it here. So now if we, you just try to look at it and just find for a given VRMS and IRMS how we proceed and calculate the parameters. So just have a look over it. I give you 3 minutes and then I will explain to you. Okay. So for the complex power, we have the VRMS, IRMS conjugate. So we take the value of this I with the negative sign to take the conjugate value. And we find the complex power. And the magnitude of this complex power is the apparent power, which is 44 volt ampere. So real and reactive power can be calculated from the complex power if you write this in the rectangular form. If you just write it in the rectangular form, so it is in fact is P and Q. P is in watts and Q is in var. Power factor, you can calculate the cosine of this angle or this complex power angle. So that is 0.342 lagging. So Z is VRMS, IRMS, and that is 110 at the angle of 85° divided by 0.4 at the angle of 15°. So that is 275 at the angle of 70°. So if you want to calculate the resistive and reactive part of the impedance, so you will just convert this into the rectangular form, and in the rectangular form you can find the resistive part and the reactive part of the impedance. So you have seen now This will help you to learn further. So I just leave two problems for you for assignment, the similar problems. So one is this, you have a voltage source and you have the load which draws the RMS current of this value, and you have to calculate these values. So the same problem we have, I have shown you earlier. I have tell you the method how to solve this. So you have to calculate the power factor, parent power, active power, and reactive power. And in another example, the load draws 12 kVA at a power factor of 0.856 lagging. So it means the load draws that much power at this power factor. If the RMS value of the voltage is 120. So you have to calculate the average and reactive powers delivered to the load, peak current, and the load impedance. So you have to solve this problem. Now I just tell you the method of power factor correction. So power factor is in fact reflecting that how much power the load is drawing from the source. Actually, if your network provider or your electricity network owner will charge you for the amount of current drawn by the load installed at your premises. So if the power factor is lower, so you have the power drawn from the network is higher. So it means that the power factor is between some point 0 to 1, and if it is decreased from 1 to some lower value, so the amount of current drawn will be higher. So the nature of your load is inductive. So that inductive load will decrease the power factor, and the amount of current drawn will be increased. So we want to improve the power factor by installing capacitor in parallel to the inductive loads, to improve the power factor towards unity. So that is, in fact, is the power factor correction. So I'll show you the example. So we have, for example, we have the voltage and we have the current of the network. So angle increased, it means that the cosine of the angle will increased. So for theta 1, for theta 1, which is larger value, the power factor is decreased and the amount of current drawn will be increased, right? So when we install a capacitor in parallel, that decrease the power factor, increase the power factor and decrease the value of angle. So between voltage and current. So that is in fact the current drawn by the load is decreased by installing the capacitors in parallel. That parallel capacitors are also called shunt capacitors. So in fact they have improved the power factor of your angle. So this is called power factor correction. So when your network will draw less current, so it means you have to pay less for less amount of current drawn by your load. So we see that, for example, in fact, we have an inductive load in nature, and what we will do that we will install a capacitor in parallel to this inductive load, and by doing this, in fact, we are only affecting the power factor. We are only improving our power factor, making it towards unity. For unity, it's the ideal case, and it's purely consuming the actual power, and there is no apparent power, there is no reactive power of the network. In fact, we cannot maintain it up to the unity, but we'll try to keep it closer to unity, say 0.8. So for the power factor correction, we install capacitors, and we have to find the value of the capacitor for the improvement of the network power factor. For example, in fact, the original reactive power is Q1, and we want to move it to Q2. So that is, in fact, is the reactive power added by the capacitor. So that much power is Q1 minus Q2, and that Q1 and Q2 is calculated from this, that the power, real power is S1 cos theta 1, and the reactive power is S1 sine theta 1, right? So what we will do, the value of S1 is P cos theta 1. So we substitute S1 as P cos theta 1. So we will get the value of P tangent theta 1. So Q2 is P tangent theta 2, and we take P common and we have tangent theta 1 minus tangent theta 2. So this will give you how much VAR we can improve by installing capacitor. And once we calculate the value of the VAR, then we find the value of the capacitance. And we know that the value of VAR is Vrms square divided by the reactance. Because we will not take the impedance because it is QC. So we only take XC. So if it is P, we will take it here R, right? So this value is omega C Vrms square. So C is QC P tangent theta 1 minus tangent theta 2 omega Vrms square. So this is the value of the shunt capacitor we install in parallel to the inductive load. So we have the RMS voltage of the network is 120 volt, and the frequency of the power line network is 60 hertz, and the load absorbs 4000 watt at a lagging power factor of 0.8. So we want to improve the power factor of the network or of the load is 0.95. So what value of capacitor we need to install? What value of capacitor we need to install? So 0.8 power factor means that the value of theta 1 is 36.87 degree, and the apparent power we can calculate by P by cos theta 1. So this is in fact is 4000 divided by 0.8 is 5000 volt ampere. From this we calculate the Q1. So similarly, we follow the same steps to find it for the value of 0.95. So we find the value of Q2 here, and the difference of Q1 and Q2 is QC. So we find the value of QC, and from this we will find the value of QC omega Vrms square. And you know the omega is 2 pi f, f is 60 hertz, and Vrms is 120 volt. So the value of capacitor is 310.5 microfarad. Now we have to also consider the voltage rating for the capacitor. Here the RMS voltage is 120 volt. So the peak value of the voltage is under root 2 Vrms. So that is 170 volt peak. So now for a safer side, we choose the capacitor for voltage rating of 200 volt. So that's the bit introduction about complex power triangle, and the power factor improvement method by installing capacitor of suitable capacity, suitable value, and voltage rating.